Most of our planet is covered by water. More than 97% of our planet's water occurs as ocean salt water. Most of the remaining water is stored in glaciers and ice sheets and groundwater. Only 0.001% is located in the atmosphere. Water is able to shift between states, solid, liquid, and gaseous, very easily. It is constantly cycled between the reservoirs via the atmosphere. Some of these transitions require energy, such as evaporation, melting, or sublimation. Others release energy, such as condensation, freezing, or deposition. Evaporation occurs if energy is available to a water surface. The water vapor in the air increases as surface water evaporates. The maximum possible amount of water vapor in the air is defined as saturation. Saturation marks an equilibrium between evaporation and condensation. Here is another way that will help you understand the concept of saturation. If you have a sealed container containing only liquid water, over a very short period of time, water molecules begin to escape from the liquid. The pressure due to the water molecules in the water vapor phase is called vapor pressure. As more and more water molecules exist in the vapor state, the condensation rate increases. If the evaporation rate equals the condensation rate, the number of water molecules in the vapor state remains constant. The pressure due to this constant amount of water vapor is called equilibrium vapor pressure or saturation vapor pressure. Humidity is the amount of water vapor in the atmosphere. Warm air can hold more water vapor than cold air. Cold, dry air can have close to 0% water vapor, while warm tropical air may have 4 to 5%. Humidity is expressed in a variety of ways. All indices refer solely to the water vapor and exclude liquid or frozen states. For example, you can express the amount of water vapor in the air through the specific humidity. Specific humidity is expressed as the mass of water vapor relative to air mass. So grams of water per kilogram of air. The maximum possible specific humidity is a function of the air temperature. It is named saturation specific humidity. An increase in temperature causes an exponential increase in saturation specific humidity. For example, at a temperature of -10 degrees Celsius, the air can hold a maximum of 2 gram water vapor per kilogram air. At a temperature of 20 degrees Celsius, the air can hold a maximum of 15 gram water vapor per kilogram air. Closely related to specific humidity is the mixing ratio, which expresses the mass of water vapor relative to dry air mass. The dew point is the temperature at which saturation occurs in air. It is an indicator of moisture content in air because high dew points indicate abundant atmospheric moisture. For example, air that contains 26 gram of water vapor per kilogram air has a dew point of 30 degrees Celsius. Relative humidity refers to the amount of water vapor in the air relative to the possible amount, which is defined by the saturation. That implies that if you change the temperature of the air, you automatically change its relative humidity, even though its water vapor content might be the same. For example, if you increase the air temperature, you increase its ability to hold water vapor, and by that you decrease its relative humidity. For example, A relative humidity of 50% means that the air contains half the amount it could at a given temperature. You get 50% of relative humidity if 1 kilogram of air at negative 10 degrees Celsius contains 1 gram of water vapor, or if 1 kilogram of air at 20 degrees Celsius contains 7.5 gram of water vapor. If the amount of water vapor in the air remains constant, the relative humidity will change in the course of a day. Air temperatures are low early in the morning. Consequently, the saturation-specific humidity will be low and the relative humidity will be high. Air temperatures are high in the afternoon. Consequently, the saturation-specific humidity will be high and the relative humidity will be low. You can measure humidity with a psychrometer. A psychrometer consists of a wet bulb and a dry bulb thermometer. Unsaturated air facilitates evaporation and consequently cooling at the wet bulb thermometer. The difference between the wet bulb and the dry bulb temperature is an indication for the humidity content of the air. The larger the difference, the drier the air. Modern methods of measuring humidity apply electronic sensors. Sensors that measure the changes in the electric resistance or the electric field as a result of changes in humidity. Unsaturated air, meaning air that has a relative humidity of less than 100%, can achieve saturation in 3 ways. Number 1. Addition of water vapor to the air at a constant temperature. That happens, for example, when light fogs forms beneath clouds as vapor is added through falling raindrops. Number 2. Mixing cold air with warm, moist air, which happens, for example, with contrails or with steam fog. And number 3. The cooling of air to the dew point, which is the most common way. When saturation of air is achieved and condensation takes place, it can produce various forms of condensation. Dew occurs after condensation takes place on surface objects. Surface air is typically cooled through terrestrial radiation loss on calm, cool, clear nights. The surface air becomes saturated and condensation occurs on objects which are acting as condensation nuclei. Frost is similar to dew, except that it forms when surface temperatures are below freezing. In this case, deposition occurs instead of condensation. The product is also called white or hoar frost. Frozen dew occurs when the dew formation is followed by a temperature drop below freezing point. This process causes a tight bond between ice and the surface, which is called black ice on roadways. Fog is basically a cloud with a base at or very near the ground. Physically, there is no difference between a stratus cloud and fog. They have the same appearance and structure. The difference is in the method and place of formation. Clouds generally occur when air rises and cools by expansion. Fog generally forms by cooling of air from cold surfaces or addition of water vapor. Radiation fog occurs when near-surface air chills to saturation, typically through terrestrial radiation loss on clear, cool nights. After sunrise, the fog evaporates due to surface heating. This illustration shows how radiation fog is formed. Air containing fog is relatively cold and dense. It drains downslope in hilly terrain and accumulates in valleys, where it is also called valley fog. Here you see how valley fog is formed. Advection fog forms when warm, moist air moves across a cooler surface and the air is chilled to saturation. It is a common phenomenon on the US West Coast, when warm, moist air from the central Pacific advects over the cold California ocean current. It frequently develops near boundaries of opposing ocean temperatures, such as off the northeast coast of the United States. Upslope fog is the only fog that is developed through adiabatic cooling, which is cooling by the expansion of air. Air is advected over land surfaces, which increase in elevation. It is a common phenomenon in the Great Plains of the US when warm, moist air advects from the Mississippi River Valley towards the Rocky Mountains. Evaporation fog or steam fog occurs when cool air moves over warm water. The warm water evaporates and saturates the air above, which causes condensation and rising air. It is common over lakes on clear, crisp mornings. Frontal fog or precipitation fog occurs when warm air is lifted over cold air. The associated cooling of the warm air causes condensation, cloud formation, and rain. The raindrops evaporate partly on their way to the ground, and condensation will cause fog if the lower cold air is near the dew point.